Hello, my friend. Tonight we'll explore the quiet power of thermodynamics, the science of heat, energy, and change. These are the laws that guide engines, stars, and even the rhythm of your own body. If this is your first time here, know that these videos are designed not just to teach, but to help you drift gently into sleep. So settle in, get comfortable, and let the story of energy and entropy carry you through the night. Let's begin. Chapter 1. What is thermodynamics? A quiet introduction. Thermodynamics is the science of energy, heat, and transformation at the scale of everyday experience. It explains how systems exchange energy with their surroundings, which changes happen spontaneously, and which changes require outside help. Unlike mechanics, which tracks the detailed motion of particles, thermodynamics speaks in the language of bulk properties, temperature, pressure, volume, and composition, and from them draws general conclusions that apply across materials and scales. A kettle cooling on the counter, a thundercloud forming over warm water, a lithium-ion battery propelling an electric car, and a star shining for billions of years are all governed by the same thermodynamic principles. Any thermodynamic discussion begins by specifying a system, the part of the world we intend to analyze, and separating it from its surroundings. The boundary between them can be a steel wall, the moving face of a piston, a semi-permeable membrane, or simply an imaginary surface drawn through air or water. If neither matter nor energy crosses the boundary, the system is isolated. If energy but not matter crosses, the system is closed. If both energy and matter cross, the system is open. These categories are not just labels, they determine what balances must hold. A closed pressure cooker can heat and cool, exchanging energy but not steam. A living cell is open, importing nutrients and exporting waste while continuously exchanging heat. A well-insulated container is designed to behave approximately as an isolated system for the duration of an experiment. The macroscopic state of a system is summarized by state variables. Some are extensive, scaling with system size, such as internal energy, entropy, and volume. Others are intensive, independent of size, such as temperature, pressure, and chemical potential. When a system is in mechanical, thermal, and chemical equilibrium, its state variables are uniform in space and stable in time. In that condition, they obey relations called equations of state. The ideal gas is the simplest example. Pressure, volume, and temperature are linked in a way that does not depend on the specific gas, provided interactions are weak. Real gases in condensed phases deviate from ideality, but the principle holds. Once enough state variables are specified, the rest follow, and the macroscopic behavior becomes predictable without microscopic detail. Thermodynamic processes move systems from one state to another. A process may be slow and carefully controlled, keeping the system arbitrarily close to equilibrium at each step, or it may be rapid, driving turbulence and strong gradients. The ideal limit of a perfectly controlled, infinitely slow process is called reversible. No real process is truly reversible. Friction, viscosity, and finite temperature differences always introduce dissipation. Yet the reversible limit is invaluable because it sets the best possible performance and provides a clear benchmark. In practice, we also describe processes by constraints. An isothermal process proceeds at constant temperature, an isobaric process at constant pressure, an isochoric process at constant volume, and an adiabatic process with no heat transfer. These names say nothing about speed, only about what is held fixed while the system changes. Energy crosses boundaries in two distinct modes: heat and work. Heat is energy transfer caused solely by temperature difference. Work is energy transfer associated with organized forces acting through distances or with generalized forces such as electrical, magnetic, and surface forces. A moving piston does pressure volume work, an electric motor does electrical work. Stretching a membrane or magnetizing a core are additional work modes. Heat itself travels by three mechanisms. Conduction transmits energy through matter by the vibrations and motions of particles. Metals conduct strongly because mobile electrons carry energy efficiently. Convection transports heat by the bulk motion of fluids. A warmed parcel of air rises and transfers energy as it moves. Radiation carries energy by electromagnetic waves and needs no material medium. This is how sunlight warms Earth across space. Real systems often combine all three mechanisms at once. Temperature, so familiar in daily life, gains sharp meaning from the Zeroth law of thermodynamics. It states that if system A is in thermal equilibrium with system B and B with C, then A and C are also in equilibrium. This transitive property implies that a single scalar quantity, temperature, classifies thermal states and legitimizes thermometers as universal comparators. The Kelvin scale anchors temperature to absolute zero, the conceptual point where classical thermal motion would cease. We cannot reach absolute zero in practice, but fixing the zero gives a natural yardstick that simplifies equations and makes temperature measurements consistent across laboratories and technologies. The first law of thermodynamics tailors the conservation of energy to thermal systems. The change in a system's internal energy equals the heat added to the system minus the work done by the system on its surroundings. Internal energy gathers the microscopic contributions, molecular motion, interactions and bonds, electronic and magnetic excitations, into a single accounting variable. When a gas is compressed, external agents do work on it, and its internal energy rises, often raising temperature. When a hot block warms a cooler one, the combined internal energy of the two blocks stays the same while it is redistributed between them. Calorimetry quantifies these changes. In a chemical reaction, the measured heat at constant pressure is the enthalpy change. When a liquid evaporates at its boiling point, the absorbed heat is the latent heat of vaporization. These measured quantities connect directly to the first law counting and allow engineers and chemists to design processes that deliver the work or heat they desire. Conservation alone does not tell us which way change will go. The second law supplies that direction. It introduces entropy, a state function that quantifies the dispersal of energy and, more deeply, the number of microscopic arrangements compatible with the macroscopic variables. For an isolated system, entropy never decreases. It increases in spontaneous processes and remains constant only for ideal reversible changes. This statement encodes the macroscopic arrow of time. A gas left to expand into a larger container does so unprompted because the number of accessible microstates balloons when the gas occupies more volume. Two blocks at different temperatures, placed in contact, equilibrate to an intermediate temperature, because that redistribution creates many more microscopic possibilities than the initial separation. Entropy is not a mystical force. It is a precise measure that tallies possibilities. Engines and refrigerators can direct energy flows, but only by exchanging energy with reservoirs in ways that leave the total entropy budget non-decreasing. Devices that would violate this rule, perpetual motion machines of the second kind, are forbidden not by a lack of ingenuity, but by the structure of nature. At the lowest temperatures, the third law becomes relevant. As temperature approaches absolute zero, the entropy of a perfect crystal approaches a constant minimum characteristic of its ground state. Careful measurements of heat capacities and other low-temperature properties support this statement and imply a practical rule. Absolute zero cannot be reached by any finite sequence of operations. Cooling becomes progressively more difficult as thermal energy dwindles. In this regime, quantum effects dominate behavior. Materials can become superconducting, conducting electricity without resistance, and some liquids become superfluid, flowing without viscosity. These phenomena sound exotic, yet they fit comfortably within the thermodynamic framework when the microscopic rules are supplied by quantum mechanics. Thermodynamic reasoning becomes especially compact when expressed in terms of potentials that already account for environmental constraints. When temperature and volume are fixed, the Helmholtz free energy decreases in spontaneous changes and reaches a minimum at equilibrium. When temperature and pressure are fixed, as is common in chemistry and biology, the Gibbs free energy plays the central role. A reaction or phase change that lowers the Gibbs free energy can proceed without external input. One that would raise it requires coupling to another process that supplies the needed downhill push. Melting at a temperature above the melting point lowers the Gibbs free energy. Freezing at a lower temperature does the same. Batteries deliver electrical work because the reactions inside them reduce the Gibbs free energy of the reagents, and the difference can be drawn off through a circuit. Phases and their transitions give especially vivid illustrations of thermodynamic logic. Heat ice at constant pressure, and its temperature rises until the melting point is reached. Additional energy then goes into reorganizing molecular structure rather than raising temperature. The absorbed energy is the latent heat of fusion. Continue heating the liquid to the boiling point, and the next dose of energy becomes the latent heat of vaporization. Phase diagrams map the stable states across temperature and pressure, showing the lines where phases coexist and the critical point where the distinction between liquid and gas disappears. Near criticality, fluctuations swell and substances show universal behavior independent of microscopic detail. Thermodynamics captures the macroscopic consequences even as statistical mechanics provides the molecular explanation. Although classical thermodynamics emphasizes equilibrium states and the differences between them, the world often operates away from equilibrium, driven by gradients in temperature, concentration, and velocity. Close to equilibrium, simple linear laws relate fluxes to driving forces. Fourier's law connects heat flux to temperature gradient. Fick's law connects particle flux to concentration gradient, and Newton's law connects momentum flux to velocity gradient through viscosity. Symmetry relations among these transport laws reveal deeper structure. Farther from equilibrium, the behavior can be richer. Fluids heated from below can form convection cells. Chemical reaction diffusion systems can generate waves and patterns, and driven systems can maintain organized structures by exporting entropy to their surroundings. None of this contradicts the second law. Order can persist locally as long as a system pays the entropy cost elsewhere. Thermodynamics also touches information. In computation, erasing a bit in a physical memory has a minimum energetic cost that must appear as heat, a limit that secures the second law when one accounts for measurement and memory in thought experiments such as Maxwell's demon. This bridge between information theory and thermodynamics matters as computing spreads into every corner of technology because it ties energy budgets to logical operations at the most fundamental level. The reach of the subject is vast. In geophysics, the atmosphere and oceans are shaped by the balance between solar heating, infrared cooling to space, and transport by winds and currents. Climate is thus an energetic problem. In engineering, thermodynamics provides absolute ceilings for the efficiency of engines, fuel cells, and heat pumps, allowing designers to judge how far a real device stands from the best that is possible and where losses originate. In chemistry and materials science, the principles of chemical potentials and free energies determine which reactions proceed, how fast phases nucleate and grow, and how mixtures separate or remain blended. In biology, organisms are open systems that maintain low internal entropy by importing energy and exporting waste. Metabolism, muscle contraction, and neural signaling all obey the same energy balances and entropy constraints. Across these fields, thermodynamics does not predict every detail. Rather, it constrains the space of possibilities and identifies the prices that must be paid. Why does thermodynamics endure through changing microscopic theories of matter? Because it is a theory of constraints that cares more about the allowed destinations and the exchanges with the surroundings than about the detailed path of the journey. When quantum mechanics arrived, it clarified heat capacities and explained low-temperature phases without overturning the thermodynamic laws. When relativity is important, energy and temperature transform in new ways. Yet the statements about conservation and irreversibility retain their force. No discovery has produced a perpetual motion machine, and none has reversed the direction of entropy increase in isolated systems. This introduction has outlined the essentials we will build on in later chapters: the definition of systems and surroundings, the distinction between state functions and path-dependent quantities such as heat and work, the physical meaning of temperature given by the Zeroth law, the conservation accountancy expressed by the first law, the directional bias and limits set by the second, and the behavior near absolute zero codified by the third. It has pointed toward measurement, heat transfer mechanisms, phases and their transitions, chemical potentials and free energies, transport in and out of equilibrium, and the wide sweep of applications from kettles to stars. Each of these topics will be deepened in the chapters that follow, where we will quantify the limits, examine idealized models, and connect the abstract statements to concrete calculations and real devices. And in the quiet hours, thermodynamics offers a sober comfort. Energy is always accounted for, yet its most ordered forms inevitably spread. Order can persist, but only by drawing on flows from elsewhere. In that gentle truth lies a view of time and change, binding the warmth of a cup in your hands to the distant fire of the stars. Chapter 2. The concept of energy, the currency of nature. Energy is one of the most fundamental ideas in all of science. It is the common measure of change, the universal currency that allows us to compare processes as different as a falling rock, a glowing light bulb, or a cell dividing inside a human body. In thermodynamics, energy is not simply an abstract number. It is the very quantity whose transformations define what is possible. To understand why engines work, why living systems survive, and why stars shine, one must understand energy and how it is conserved, transferred, and transformed. The modern concept of energy was not always obvious. For much of history, philosophers and scientists treated heat, motion, and chemical processes as unrelated phenomena. In the 17th century, the mechanical view of the world gained traction. Motion was seen as the basic ingredient of nature, and explanations often reduced to how bodies moved and collided. But with the rise of steam engines in the 18th and 19th centuries, a deeper unifying principle emerged. Engineers realized that the work done by an engine depended not only on the forces and displacements of pistons, but also on the amount of heat supplied by burning fuel. Careful experiments, like those by James Joule, demonstrated that heat and mechanical work could be exchanged in fixed ratios. From this grew the conviction that there is a conserved quantity, energy, that can flow in different guises but is never destroyed. In thermodynamics, energy within a system is called internal energy. This is the sum of all microscopic kinetic and potential contributions of molecules and atoms. It includes the motions of molecules as they translate, rotate, or vibrate, as well as the stored energy in chemical bonds and intermolecular forces. Internal energy is not something one can measure absolutely. What matters is the change in internal energy as a system undergoes a process. When you heat a gas, the added energy increases molecular motions, and the internal energy rises. When a chemical reaction occurs, the difference in bond energies between reactants and products appears as a change in internal energy that can manifest as heat or work. Energy is exchanged between a system and its surroundings in two distinct ways, as heat and as work. Heat is disordered energy transfer caused by a temperature difference. It is not a substance that flows, but rather the migration of microscopic motion from faster-moving particles to slower ones. Work, in contrast, is organized energy transfer, a piston being pushed, a turbine turning, or an electric current moving through a wire. Both heat and work alter a system's internal energy, but they are not properties of the system. They are processes, ways energy moves across boundaries. A system does not contain heat or work, it contains internal energy. This distinction may sound abstract, but it has practical meaning. Consider compressing a gas. If you push down the piston quickly, the work done on the gas increases its internal energy, raising its temperature. If you instead heat the gas by placing the container over a flame, the energy enters as heat. In both cases, the internal energy grows, but the pathway is different. This is why energy is the conserved currency, while heat and work are transactions that depend on how the change happens. Energy is also associated with different macroscopic forms that we recognize in everyday life. Kinetic energy is the energy of motion proportional to the mass and speed of an object. Potential energy is stored by virtue of position or configuration, such as a rock on a cliff or a compressed spring. Chemical energy is stored in the arrangement of electrons and nuclei in molecules. Nuclear energy is bound in the nucleus of atoms, released in fission and fusion. Thermal energy reflects the microscopic kinetic energies of molecules, observed macroscopically as temperature. Electromagnetic energy exists in light and radio waves. Though diverse in appearance, all of these are exchangeable and additive. One can transform into another, but the total sum remains unchanged. In thermodynamics, one particularly important form is enthalpy. Enthalpy combines internal energy with the energy associated with the system's pressure and volume. At constant pressure, the change in enthalpy equals the heat absorbed or released by a process. This is why chemists tabulate enthalpies of reaction and engineers calculate enthalpies of vaporization or combustion. Enthalpy connects the abstract balance of the first law to quantities directly measured in laboratories and power plants. When water boils, the heat input at constant pressure is exactly the enthalpy of vaporization, a measure of the energetic cost of separating molecules from liquid to gas. Another key form is free energy, which blends internal energy and entropy into a single function that predicts spontaneity under given constraints. At constant temperature and pressure, The Gibbs free energy change tells whether a reaction or phase change can occur without outside help. A negative Gibbs free energy means the process can proceed spontaneously, while a positive value signals it will not occur unless driven by coupling to another change. Free energies thus translate the bookkeeping of energy into predictions of feasibility. They will appear repeatedly in later discussions of chemical reactions, biological metabolism, and material science. To see energy's universality, one can look at examples across scales. The photosynthesis that powers nearly all life on Earth converts electromagnetic energy from sunlight into chemical energy stored in sugars. When animals eat, they oxidize those molecules, releasing energy that becomes motion, heat, or work done by muscles. In a power station, the chemical energy of fuel is transformed into heat, which produces steam, which drives turbines, which turn generators, producing electrical energy. That electricity can then light a lamp, convert to thermal radiation, and finally disperse into the environment. In every step, the forms of energy change, but the total energy remains constant. This is the essence of conservation. Energy is neither created nor destroyed. It only shifts form from concentrated and usable to dispersed and less useful. That dispersion is what entropy measures, and it explains why energy, while conserved, is not equally available for work in all circumstances. But even before introducing entropy in detail, the conservation principle itself has profound implications. It means no machine, no matter how clever, can produce work from nothing. It means perpetual motion devices of the first kind are impossible. It means that if an object cools, something else must warm. If a system accelerates, some energy source must be tapped. Measuring energy has always been a challenge because it comes in many forms. Calorimetry is the science of measuring heat changes in processes. A simple calorimeter can determine the energy released by a chemical reaction, while sophisticated differential scanning calorimeters measure phase transitions with exquisite precision. Electrical energy is measured through currents and voltages, mechanical energy through forces and displacements. Yet all these measurements are interconvertible. A joule of mechanical work is equal to a joule of heat or a joule of electricity. The universality of the unit reflects the underlying unity of energy itself. The practical importance of energy as a currency is hard to overstate. Modern civilization depends on its controlled transformation. Engines convert chemical energy to motion. Power plants convert chemical or nuclear energy to electrical energy. Refrigerators convert electrical work into thermal energy transfer, moving heat against its natural gradient. On the biological side, metabolism converts the chemical energy of food into ATP, a molecular carrier that fuels cellular work. At every level, energy serves as the accounting tool that keeps processes consistent with the laws of nature. One subtle point in thermodynamics is that the absolute amount of internal energy is not measurable. Only changes matter. This is similar to how altitude can be defined relative to sea level, but has no absolute meaning in the void of space. What counts are the differences, which determine whether energy will flow, whether work can be done, and whether a process can proceed. The choice of reference is arbitrary, but the differences are objective. The unifying role of energy extends even into fields that may seem far removed from thermodynamics. In relativity, energy and mass are equivalent, two sides of the same coin. The energy of a system includes not just motion and interactions, but also its rest mass. This equivalence explains why nuclear reactions release such enormous energies. A small change in mass corresponds to a vast change in energy. In information theory, energy constraints appear through the cost of erasing or storing information, showing that even the logic of computation has a thermodynamic price. These connections reinforce the idea that energy is not a parochial concept of physics, but a deep principle that underlies all change. Historically, understanding energy transformed science itself. Joule's careful experiments in the 1840s, stirring water with paddles powered by falling weights, showed quantitatively how mechanical work became heat. Hermann von Helmholtz formalized the conservation principle, declaring that energy can neither be created nor destroyed. Rudolf Clausius tied these insights to the developing theory of entropy. From these efforts arose a coherent thermodynamic framework that engineers could apply to engines, chemists to reactions, and physicists to the cosmos. The notion of energy unified diverse phenomena and remains the backbone of modern science. In daily life, the effects of energy are so common that we rarely pause to consider them. When you feel warmth from the sun on your skin, electromagnetic energy is being absorbed and converted to internal energy in your body. When you eat breakfast, the chemical energy in carbohydrates is released in your cells, fueling motion and maintaining body temperature. When you drive a car, the fuel's chemical energy is transformed into heat and mechanical work that turns wheels. Even the act of thinking is powered by electrical potentials across neural membranes, maintained by metabolic energy. All of these processes are simply transformations in which energy moves from one form to another, always conserved, always accounted for. In thermodynamics, energy is sometimes described as the capacity to do work. This phrase captures its practical significance, but does not fully convey its universality. Energy is the thread that connects every event in nature. The first law guarantees that it is conserved. The second law dictates how it becomes more or less useful. Later chapters will explore efficiency, entropy, and ultimate limits, but for now the key point is that energy is the measure of change itself. Without it, nothing moves, nothing warms, nothing transforms. Reflecting on energy as the universal currency can inspire a quiet existential thought. All the warmth of your body, the power of your thoughts, and the light of the stars above are parts of one continuous bookkeeping. Energy never disappears, it only flows and changes form. In this way, the same currency that fuels the fusion reactions in the sun flows into your breakfast, into your muscles, and into the words you now read. Thermodynamics tells us that though our individual arrangements are fleeting, the energy itself endures, linking us to every process in the universe. Chapter 3. The Zeroth Law, Defining Temperature. Among the four great laws of thermodynamics, the Zeroth Law may appear the most modest. It does not speak of conservation, entropy, or ultimate limits, but rather of a simple relational property, thermal equilibrium. Yet without this law, the very concept of temperature would lack coherence. The Zeroth Law provides the foundation for all thermal measurement and comparison, allowing us to say with confidence that one object is hotter, colder, or equally warm as another. Its simplicity conceals its power because it enables one of the most universal and indispensable quantities in science. The origin of the name Zeroth Law is telling. The first, second, and third laws were formulated in the 19th and early 20th centuries. Only afterward did physicists realize that an even more basic statement was required, one that underpinned all the others. Rather than renumbering the established sequence, they christened this principle the Zeroth Law, placing it before the first. Its role is to assert transitivity. If System A is in thermal equilibrium with System B and System B with System C, then A and C are in equilibrium with each other. This statement ensures that temperature is a meaningful property, one that can be assigned consistently across systems and used as a universal comparator. To grasp why this is necessary, consider what thermal equilibrium means. When two systems are brought into contact, such that they can exchange energy as heat but not matter, they may initially alter one another's internal energies. A hot object in contact with a cold one will transfer energy until no net flow of heat occurs. At that point, they are said to be in thermal equilibrium. If the zeroth law did not hold, we might find paradoxical situations in which A equilibrates with B and B with C, yet A and C, when brought together, still exchange heat. This would undermine the idea of temperature as a transitive, measurable variable. By affirming transitivity, the zeroth law allows us to construct temperature scales and to trust that measurements are transferable. From a practical standpoint, the zeroth law justifies the existence of thermometers. A thermometer is a system whose property, such as the length of a column of mercury, the resistance of a metal wire, or the voltage across a semiconductor junction, varies with temperature. By bringing the thermometer into equilibrium with another system, we let both reach the same temperature. The thermometer then serves as a proxy, giving us a numerical reading that characterizes the system's thermal state. The zeroth law ensures that this reading will be consistent. If two objects are in equilibrium with the thermometer, they must also be in equilibrium with each other. Without this guarantee, temperature readings would be ambiguous and unreliable. Temperature, however, is more than a convenient scale. It is a fundamental intensive variable that dictates the direction of heat flow. Heat flows spontaneously from the hotter to the colder body, never the reverse unless external work is done. To define hotter and colder, we rely on temperature. The zeroth law allows us to arrange systems along a single ordered scale, such that energy transfer always occurs in one direction along that scale. It gives thermodynamics its compass, pointing toward the natural direction of change. The practical art of temperature measurement has a long history. Ancient peoples sensed hot and cold with touch, but subjective feeling is unreliable and nonlinear. A lukewarm bowl may feel cool to one hand and warm to the other if they were previously immersed in different baths. The development of thermoscopes in the 17th century, simple devices using air expansion to move water levels, marked the first step toward objective measurement. Over time, scientists realized the need for fixed points to calibrate scales, such as the freezing and boiling points of water under standard pressure. Fahrenheit and Celsius introduced scales based on such points, while Kelvin later formalized the absolute scale rooted in thermodynamic principles. The Kelvin scale deserves emphasis, for it reflects the most fundamental understanding of temperature. 0 Kelvin, or absolute zero, represents the unattainable limit where the classical motion of particles would vanish. Temperature differences on this scale directly relate to energy differences in microscopic motions, making the Kelvin scale natural for theoretical and practical use. The Celsius scale is convenient for daily life, but in scientific work, Kelvin is standard. The zeroth law justifies the very existence of such a consistent scale. Modern thermometry has grown far beyond glass tubes of liquid. Resistance thermometers exploit the predictable change of electrical resistance with temperature in metals. Thermocouples generate voltages proportional to temperature differences between junctions of dissimilar metals. Infrared thermometers measure thermal radiation to infer temperature without contact. At very low temperatures, specialized methods such as noise thermometry, magnetic susceptibility, or even Doppler broadening of spectral lines become necessary. Yet in every case, the Zeroth law provides the logical basis. The property of the thermometer is compared to that of the system by establishing equilibrium, or by inferring it through radiation exchange. The Zeroth law also introduces an important conceptual point. Temperature is an intensive property, independent of the size of the system. If 2 liters of water at 20 degrees Celsius are combined with another 2 liters at the same temperature, the result is still at 20 degrees Celsius. This is different from energy, which is extensive and doubles with the doubling of mass. The distinction between intensive and extensive variables is one of thermodynamics' most useful organizing principles, and temperature exemplifies the intensive class. Although the Zeroth law appears self-evident, its implications are profound. It allows temperature to serve as the parameter linking systems across physics, chemistry, and biology. In chemical reactions, equilibrium constants depend on temperature. In biology, enzymes operate optimally only within narrow temperature ranges, reflecting the sensitivity of biochemical equilibria. In astrophysics, the thermal equilibrium of a star's core determines its luminosity and lifespan. In engineering, every process, combustion, refrigeration, metallurgy, depends on careful control of temperatures. All of this rests on the simple assurance that temperature can be defined consistently. One might ask whether the Zeroth law is truly independent or whether it could be derived from the other laws. In fact, it is independent. The first law conserves energy but does not define temperature. The second law introduces entropy and directionality, but presumes the existence of temperature to define entropy changes. The third law addresses behavior near absolute zero, but likewise assumes the concept of temperature is valid. The Zeroth law alone ensures that temperature is well defined in the first place. This independence is why it stands as a separate principle, modest in appearance, but essential in structure. Temperature also connects macroscopic thermodynamics with microscopic statistical mechanics. In statistical terms, temperature is related to the distribution of energies among particles. A system at high temperature has energy distributed widely, with particles occupying higher energy states. At low temperature, particles cluster in lower energy states. The Zeroth law guarantees that systems exchanging energy will reach a common distribution, which macroscopically appears as equal temperatures. This bridge between the microscopic and the macroscopic is one of the most elegant features of physics. In non-equilibrium situations, where gradients of temperature exist, energy flows to restore equilibrium. The Zeroth law describes the endpoint of that process, equality of temperature. Engineers and scientists use this knowledge to design systems that exploit gradients before equilibrium is reached. Heat engines, refrigerators, and power stations all operate because they maintain temperature differences between components. When equilibrium is achieved, no further useful work can be extracted. Thus, the Zeroth law not only explains measurement, but also defines the ultimate limit of thermal exploitation. Another subtlety is the role of temperature in defining thermodynamic potentials. Free energy functions, used to predict spontaneity, include temperature as an explicit variable. Without the Zeroth law, we could not assign a single temperature to a system and use it in such expressions. In practice, when a system is not at uniform temperature, it cannot be fully characterized by a single thermodynamic state. This limitation highlights why equilibrium is so central to thermodynamics. Only in equilibrium can we assign global values to temperature and other variables, enabling the use of simple laws. Beyond practical applications, the Zeroth law has philosophical significance. It shows that some truths about nature are relational rather than absolute. Temperature is not a substance or a hidden essence. It is a comparative property arising from how systems interact. The law does not tell us what temperature is in itself, but what it does. It organizes systems into equivalence classes of equilibrium. It is a reminder that many physical quantities are defined operationally through their measurable consequences rather than by some intrinsic meaning. In daily experience, the effects of the Zeroth law are ubiquitous. When you take your body temperature with a thermometer, you rely on the principle that your body and the thermometer, once in equilibrium, share the same temperature. When a baker adjusts an oven, the entire loaf will eventually reach the oven's set temperature because equilibrium demands it. When a physician sterilizes instruments in boiling water, the assurance is that water at a given pressure always boils at the same temperature, reproducibly and consistently. All these actions, from the ordinary to the critical, rest silently on the Zeroth law. The law also frames the limits of perception. Human senses detect hot and cold but cannot quantify them consistently. The Zeroth law, combined with instruments, extends our perception to extremes. The near absolute zero of laboratory cryogenics, the millions of degrees in stellar cores, and the delicate temperature differences in climate systems that drive weather. Without the Zeroth law's assurance, these measurements would be no more than guesses. Ultimately, the Zeroth law is about coherence. It assures us that temperature is a real, consistent, measurable property that organizes matter and energy into an ordered scale. It allows us to construct instruments, calibrate processes, and compare conditions across time and space. It ties together the everyday language of warmth and cold with the precise framework of physics. And in the quiet reflection that ends this introduction, the Zeroth law carries a subtle existential message. It tells us that in the vast variety of systems, from stars to cells, there is a universal measure that links them: temperature. It whispers that equilibrium is the common destiny of all systems allowed to interact freely. In that leveling lies a gentle reminder that while complexity and difference flourish for a time, nature has a way of smoothing them into balance, carrying all things toward a shared stillness. Chapter 4. The first law of thermodynamics: energy cannot be created. The first law of thermodynamics is often stated in a deceptively simple way: energy cannot be created or destroyed. This sentence, almost axiomatic in its brevity, captures a principle that applies to every event in the universe, from the burning of a candle to the birth of a galaxy. The first law is the formal expression of energy conservation adapted to thermal processes. It tells us that although energy may change form, flow across boundaries, or disperse into less useful modes, the total quantity remains constant. The roots of this law lie in the 19th century, during the age of steam engines and industrial expansion. Engineers were obsessed with efficiency, how much work could be extracted from burning coal, and how much was lost as waste heat. In this context, James Joule's meticulous experiments demonstrated that mechanical work and heat are interchangeable in fixed proportions. By stirring water with paddles driven by falling weights, Joule measured how the water's temperature increased. He showed that a given amount of mechanical work always produced the same increase in thermal energy, regardless of the method. His work proved that heat was not a substance that flowed, but a mode of energy transfer. Around the same time, Rudolf Clausius and William Thomson, later Lord Kelvin, formalized this into the conservation principle that became the first law of thermodynamics. In its most general form, the first law relates the change in a system's internal energy to the energy that crosses its boundary as heat or work. Internal energy is a comprehensive term encompassing all microscopic motions and interactions inside the system. Molecular vibrations, rotations, translations, bond energies, and other contributions. When the system absorbs heat, its internal energy rises. When it does work on its surroundings, its internal energy falls. Conversely, when work is done on the system, its energy increases. This balance sheet never fails. The change in internal energy always equals the net energy transferred in. The importance of this statement becomes clear in practical examples. Consider compressing a gas in a piston. If the compression is rapid and insulated, no heat escapes, so the work done on the gas directly increases its internal energy, raising its temperature. If instead the gas is compressed slowly while in contact with a thermal reservoir, the heat can flow out and the temperature may remain constant. In both cases, the first law tracks the energy balance, but the pathway, the division between heat and work, differs. The law thus distinguishes between state functions like internal energy, which depend only on the current state, and process-dependent quantities like heat and work, which depend on how the change occurs. This distinction is essential. A system does not contain heat or work in the way it contains internal energy. Heat and work are not properties but processes, ways energy moves across boundaries. Misunderstanding this leads to common misconceptions, such as describing heat as a substance. The first law makes clear that heat is energy in transit due to a temperature difference, and work is energy in transit due to forces acting through displacements or other generalized coordinates. The bookkeeping is unambiguous once these definitions are recognized. The first law is not limited to mechanical work and thermal energy. It applies equally to electrical work, surface work, magnetic work, and other generalized forms. For instance, when a battery drives current through a circuit, the electrical work done equals the chemical energy decrease in the battery, plus any heat generated by resistance. In a stretched rubber band, the work associated with elongation alters internal energy stored in molecular configurations. In magnetic systems, aligning domains requires magnetic work. The first law encompasses them all, recognizing only that energy flows in and out, but never appears from nothing. Chemistry offers another vivid illustration. In an exothermic chemical reaction, bonds in the reactants rearrange into more stable configurations, releasing energy. That energy may appear as heat, warming the surroundings, or as work, perhaps driving a piston. In an endothermic reaction, energy must be supplied to form products of higher internal energy. In both cases, the total energy of the universe remains unchanged. By defining enthalpy, a related thermodynamic quantity, chemists can calculate the heat released or absorbed under conditions of constant pressure, which is the most common laboratory setting. Combustion reactions, neutralizations, and phase changes are thus all described within the framework of the first law. In biological systems, the same principle holds. Cells extract chemical energy from food, storing it temporarily in molecules like ATP. Breaking down ATP releases energy that powers muscle contraction, nerve impulses, and biosynthesis. The energy is not created by the cell. It is transformed from the chemical bonds of nutrients into usable biochemical work and heat. Metabolism exemplifies the conservation principle in a living context. Every joule that enters as food must eventually leave as work, heat, or stored energy. The first law also clarifies why perpetual motion machines of the first kind are impossible. Such hypothetical devices claim to produce work indefinitely without an energy source. According to the first law, this cannot happen. A machine cannot generate more energy than it receives. If a device appears to run forever, closer inspection always reveals a hidden source of energy being consumed or dissipated. The impossibility of such devices is not a matter of engineering limitation, but of physical law. At the cosmic scale, the first law still applies. Stars radiate light and heat into space, but they do not create energy from nothing. Instead, they convert nuclear binding energy into radiation. When hydrogen fuses into helium, a small fraction of mass is converted into enormous energy, consistent with Einstein's equivalence of mass and energy. The balance still holds. The star's internal store of nuclear fuel diminishes as energy flows outward. Even the expanding universe can be described in energy terms, though with subtleties arising from general relativity. The conservation principle remains central, even when space itself is dynamic. Measurement of energy changes is a central task of experimental thermodynamics. Calorimetry provides one method. A bomb calorimeter measures the energy released by combustion by observing the temperature rise of water surrounding a sealed chamber. Such measurements allow scientists to assign energy content to fuels and foods. In engineering, monitoring work and heat balances ensures efficiency and safety. Power plants are analyzed in terms of enthalpy flows and energy balances, with the first law providing the central accounting equation. From steam turbines to refrigeration cycles, the principle is applied daily in practical designs. The law also connects to statistical mechanics. From the microscopic perspective, the internal energy of a system is the ensemble average of the energies of all its microstates. When energy is transferred as heat, the populations of microstates shift. When work is done, the distribution of accessible states changes. The first law emerges naturally from this statistical framework, confirming that it is not just an empirical rule, but a consequence of deeper principles. Still, the beauty of thermodynamics is that one does not need microscopic detail to apply the law. Macroscopic balances suffice, allowing predictions without ever tracking individual molecules. It is important to note what the first law does not tell us. It does not dictate the direction of processes. A hot body cooling in a room conserves energy, but the law does not explain why the reverse does not occur spontaneously. That question belongs to the second law and the concept of entropy. The first law is silent on feasibility and irreversibility. It speaks only of balances. This limitation is why all four laws are necessary, each complementing the others. Despite its apparent simplicity, the first law underlies much of modern technology. In designing an aircraft engine, engineers calculate energy flows into and out of the combustion chamber. In renewable energy systems, the conversion of solar radiation into electricity is analyzed in terms of energy balances. In climate science, the Earth's energy budget, solar input, infrared output, and internal heat flows, is described using the first law. In medicine, the human body's energy balance determines weight change, calories in, calories out, with conservation as the unbreakable rule. The law applies universally across scales and disciplines. The elegance of the first law lies in its absoluteness. No exception has ever been observed. It survived the transition from classical mechanics to relativity, from the caloric theory of heat to quantum mechanics. Even as physics deepened its understanding of matter and fields, the conservation of energy persisted as a guiding beacon. If any experiment were to show energy appearing from nowhere, the foundations of physics would be shaken. Yet every test confirms the constancy of energy. In this way, the first law is both empowering and humbling. Empowering because it allows us to design machines, understand metabolism, and model the universe with confidence that our accounts will balance. Humbling because it reminds us that energy is not ours to create or destroy. We can only borrow it, transform it, and pass it along. Every light we turn on, every breath we take, every star that shines is participating in this endless circulation of energy, a circulation without origin or end. And in a quiet moment, one may reflect on the existential whisper behind the first law. If energy is never created and never destroyed, then the warmth in your body, the glow of a fire, and the brilliance of the sun are all transformations of something timeless. We are temporary arrangements in a universe where energy endures, reshaping itself endlessly, but never vanishing. In that continuity lies a subtle sense of permanence amid change, a reminder that though we pass, the energy that sustains us continues its journey through the cosmos. Chapter 5. The second law, the arrow of time and entropy. If the first law of thermodynamics assures us that energy is conserved, the second law reveals why not all energy is equally useful. It tells us that in every real process, energy tends to spread out, differences are smoothed away, and disorder grows. This principle is captured in the concept of entropy, a quantity that measures the dispersal of energy and the number of possible microscopic arrangements of a system. The second law is not about balance sheets alone. It is about direction. It explains why coffee cools down but never heats itself, why gases expand into available space, why machines can never be perfectly efficient, and why the universe itself evolves toward greater uniformity. The essence of the second law is simple. In an isolated system, entropy never decreases. Entropy may remain constant in idealized, perfectly reversible processes, but in every natural, irreversible process, it increases. This is the arrow of time. The first law is indifferent to direction. Energy can flow either way as long as the balance is preserved. But the second law tells us that spontaneous processes always go one way and not the other. A shattered glass will never reassemble itself. Heat will never flow from a colder object to a hotter one without external work. These asymmetries, so obvious in daily life, find their precise explanation in the second law. Entropy is sometimes loosely described as disorder, but this is an oversimplification. In a more rigorous sense, entropy quantifies the number of microstates compatible with the macroscopic state of a system. The greater the number of microscopic configurations that realize a given state, the higher its entropy. A gas confined to half a container has relatively few possible configurations. When it expands to fill the entire container, the number of accessible microstates increases enormously. The entropy rise reflects that explosion of possibilities. The idea that entropy is linked to probability was crystallized in the late 19th century by Ludwig Boltzmann. His statistical definition tied entropy to the logarithm of the number of microstates, scaled by a universal constant. This connection bridges microscopic and macroscopic worlds. At the particle level, the equations of motion are reversible. Play them forward or backward in time, and the laws look the same. But when we consider vast numbers of particles, the overwhelmingly probable direction is toward states with larger numbers of microstates. In other words, entropy growth is not a violation of microscopic laws, but a statistical certainty. The arrow of time defined by the second law is not absolute in the sense of impossibility, but practical inevitability. It is not strictly impossible for the air molecules in a room to cluster in one corner, lowering entropy, but the probability is so vanishingly small that it will never be observed. With on the order of 10 Quabb particles in macroscopic systems, the odds of spontaneous decreases in entropy are astronomically tiny. Thus, we observe entropy increase as a fundamental feature of the macroscopic world. Heat engines offer a clear application of the second law. A heat engine extracts energy from a hot reservoir, converts some into work, and releases the rest to a cold reservoir. The second law says that no engine can convert all the absorbed heat into work. Some must always be rejected. The Carnot cycle, an idealized model consisting of reversible processes, defines the maximum possible efficiency of any engine operating between two temperatures. This efficiency depends only on those temperatures, not on the working substance or the engineering design. Real engines always fall short of this maximum because irreversibilities such as friction and turbulence increase entropy further. The second law thus sets an unbreakable ceiling on efficiency, one that no technology can surpass. Refrigerators and heat pumps demonstrate the principle from another perspective. They transfer heat from colder to hotter regions, but only by consuming work. The second law prohibits the spontaneous flow of heat from cold to hot. By applying external energy, however, we can drive the process, at the cost of producing even more entropy overall. This is why cooling your home requires electricity, and why the waste heat expelled outdoors exceeds the cooling achieved indoors. Entropy growth is unavoidable, even when we temporarily reverse the natural direction of heat flow. Entropy also explains why no process can be perfectly reversible in reality. Any real process involves finite differences in temperature, pressure, or concentration that drive the change. These differences produce entropy as they equalize. A truly reversible process would require infinitesimal gradients and infinite slowness, conditions that cannot be realized. The concept of reversibility is a useful idealization for setting theoretical limits, but it is never achieved in practice. The second law extends beyond simple mechanical or thermal systems. In chemistry, it governs the direction of reactions. A reaction will proceed spontaneously when the free energy decreases, which is directly tied to entropy changes in the system and surroundings. At equilibrium, the balance of entropy contributions reaches a maximum and no net change occurs. In biology, organisms survive by exporting entropy to their surroundings, maintaining local order only by accelerating the overall growth of entropy in the environment. Life does not defy the second law. It exemplifies it by drawing on energy flows to create local structure. The second law also manifests in transport processes. Heat conduction, diffusion of particles, and viscous dissipation all represent spontaneous flows that increase entropy. A temperature gradient drives heat until equilibrium is reached. A concentration gradient drives diffusion until uniformity is established. A velocity gradient in a fluid produces frictional heating, again raising entropy. In each case, the system evolves toward a state of greater uniformity, corresponding to more microstates and higher entropy. Cosmology offers perhaps the most dramatic stage for the second law. The universe began in an incredibly low entropy state, a condition of remarkable uniformity despite its vast energy content. Over cosmic time, entropy has increased through the formation of stars, galaxies, and black holes. Remarkably, black holes have the largest entropy of any known objects, proportional to the area of their horizons. Stephen Hawking's discovery that black holes radiate thermally reinforced this link between gravity, quantum mechanics, and entropy. The fate of the universe may ultimately be dictated by the second law, a progression toward heat death, in which all energy differences are erased and no useful work remains possible. The second law also intersects with information theory. In the 20th century, scientists such as Claude Shannon realized that information has an entropy of its own, quantifying uncertainty in messages. The connection became more than metaphorical when Rolf Landauer demonstrated that erasing a bit of information carries a minimum energy cost. This insight resolved the famous puzzle of Maxwell's demon, a thought experiment in which a tiny being supposedly violates the second law by sorting fast and slow molecules. When the demon's memory and information processing are included in the balance, entropy is preserved. Thus, even in the realm of computation, the second law reigns, linking physical entropy with informational entropy. The law also influences climate science. The Earth absorbs energy from the sun at high temperature and radiates it into space at a much lower temperature. The difference sustains weather systems, winds, and ocean currents, all of which operate as mechanisms that redistribute energy while increasing entropy. The global climate is, in effect, a massive thermodynamic engine. Understanding its balance requires applying the second law alongside the first, ensuring that both conservation and directionality are respected. It is worth noting that the second law does not conflict with the conservation principle of the first law. Energy is conserved exactly, but its quality changes. The second law distinguishes between high-grade energy, capable of doing work, and low-grade energy, dispersed as heat at uniform temperature. As processes unfold, high-grade energy degrades into lower-grade forms until ultimately it is no longer useful for performing work. This distinction between quantity and quality of energy is central to thermodynamics. The universality of the second law is striking. No exception has ever been observed. Every real process leaves behind an increase in entropy, whether in engines, chemical reactions, biological metabolism, or cosmic evolution. It is not a matter of incomplete knowledge or limited engineering, but a fundamental feature of nature. Even as physics has been revolutionized by relativity and quantum mechanics, the second law has remained intact. Indeed, it has often found deeper foundations in those newer theories. Reflecting on the second law, one appreciates its philosophical depth. It explains not only physical processes, but also our very perception of time. The reason we remember the past but not the future lies in entropy's relentless increase. The past had lower entropy, allowing patterns to be imprinted, while the future is open, with more possible microstates yet unrealized. In this way, the second law underpins our experience of temporal flow. And so at the end of this chapter, the second law speaks to us not only as scientists, but as observers of existence. It tells us that everything moves toward equilibrium, that order is always temporary, and that the universe itself has a preferred direction. Yet in this continual drift toward higher entropy, structures form, lives unfold, and meaning arises, however briefly. The arrow of time carries us forward, and entropy is the silent clock that marks our passage. Chapter 6. The Third Law. The Impossible Cold. The third law of thermodynamics stands apart from the others. While the first law enshrines the conservation of energy and the second law explains direction and entropy, the third law deals with an ultimate limit, absolute zero, the coldest conceivable temperature. It tells us that as a system approaches absolute zero, its entropy approaches a constant minimum. In practice, this means that absolute zero can never be reached by any finite number of steps. However clever our methods, however powerful our cooling machines, there will always remain some fraction of thermal energy. The third law defines the ultimate boundary of cold and reveals the strange physics that emerges near that limit. To appreciate the third law, we must understand what temperature represents. Temperature reflects the average energy of microscopic motion within a system. At ordinary conditions, molecules vibrate, rotate, and translate with enormous speed. Even in a block of ice at 0 degrees Celsius, water molecules jiggle and shift positions continually. As a system is cooled, this microscopic activity diminishes. The third law says that in the limit of 0 Kelvin, a perfectly ordered crystal would have only one possible microstate, giving it zero entropy. Real substances, however, often retain residual entropy because of imperfections, disorder in atomic arrangements, or quantum effects. Thus, entropy does not always vanish entirely, but the law asserts that it reaches a well-defined minimum. Historically, the third law emerged from low-temperature studies in the late 19th and early 20th centuries. Walther Nernst, a German chemist, formulated what became known as the Nernst heat theorem. He observed that as substances cooled toward absolute zero, the entropy changes of reactions and phase transitions tended to vanish. From this, he proposed that the entropy of a pure, perfect crystalline substance approaches zero at 0 Kelvin. This idea, refined by subsequent work, became the third law. Nernst's insights earned him the Nobel Prize in Chemistry in 1920 and laid the foundation for modern low-temperature physics and chemistry. The impossibility of reaching absolute zero has profound consequences. Cooling techniques can remove thermal energy progressively, but that the closer one gets to 0 Kelvin, the more difficult it becomes. Early methods relied on evaporative cooling, where a liquid absorbs heat as it vaporizes. Later, scientists used adiabatic demagnetization, where a magnetic material's thermal energy is reduced by aligning and then randomizing its spins under controlled conditions. Today, laser cooling can slow atoms to speeds of mere centimeters per second, achieving temperatures within billionths of a degree of absolute zero. Yet even these advanced methods cannot achieve zero itself. The third law guarantees that the final step is unattainable, no matter the ingenuity. Why is this so? Each cooling step relies on some physical process that becomes less effective as temperature falls. In evaporative cooling, fewer particles have the energy to escape as the system cools. In adiabatic demagnetization, the entropy reduction saturates a spindle line. In laser cooling, residual photon recoil sets a limit. Every method faces diminishing returns, an asymptotic barrier that reflects the third law in practice. Absolute zero is a horizon that can be approached ever more closely but never crossed. Near absolute zero, matter behaves in ways that defy ordinary intuition. Quantum effects dominate because the thermal agitation that usually masks them is suppressed. Helium, for instance, remains liquid all the way down to absolute zero under ordinary pressures. Instead of freezing, it undergoes transitions into quantum states such as superfluidity, in which it flows without viscosity. Superfluid helium can climb the walls of its container and form thin films that defy gravity. Metals, when cooled below critical temperatures, can become superconductors, carrying electrical current without resistance. These phenomena, discovered in the 20th century, were among the first glimpses of macroscopic quantum effects, where the collective behavior of countless particles follows quantum rules. The third law also stabilizes the entropy scale. Because entropy changes can be measured through heat capacities and other properties, knowing that entropy approaches a finite constant at 0 Kelvin provides a reference point. Without the third law, entropy would be defined only up to an arbitrary constant. With it, chemists and physicists can assign absolute entropy values to substances, allowing precise calculations of equilibrium, free energies, and chemical potentials. This has enormous practical value, enabling predictions of reaction behavior, phase stability, and material properties. A striking consequence of the third law is the behavior of specific heats at low temperatures. For most substances, the heat capacity decreases steadily as temperature falls, approaching zero as absolute zero is neared. This makes sense. With fewer available modes of motion, the system cannot absorb much energy. The precise way in which heat capacity falls depends on the material and reveals details about its quantum states. In crystals, the Debye model describes how vibrational modes, or phonons, freeze out at low temperatures. In metals, the behavior reflects both lattice vibrations and electron excitations. These measurements not only confirm the third law, but also provide windows into the underlying physics of matter. The third law influences technology in profound ways. Superconductivity, enabled by low-temperature physics, underpins technologies from MRI machines to particle accelerators. Superfluid helium is used to cool detectors and quantum devices. Cryogenics, the science of producing and using very low temperatures, is critical for space exploration, where instruments must be cooled to detect faint infrared signals, and for quantum computing, where delicate states require extreme isolation from thermal noise. None of these applications would be possible without the understanding provided by the third law. It also imposes limits. Because absolute zero cannot be reached, there will always be some residual thermal motion. This sets a lower bound on noise in measurements, known as thermal or Johnson-Nyquist noise in electronics. In quantum computing, this residual energy threatens to disturb fragile quantum states. Engineers must design systems to work within these constraints, aware that the third law sets boundaries no ingenuity can cross. Beyond the laboratory, the third law plays a role in astrophysics. The coldest natural places in the universe, such as the shadowed craters of the moon or interstellar clouds, reach temperatures only a few degrees above absolute zero. The cosmic microwave background, a remnant of the Big Bang, bathes the universe at about 2.7 Kelvin. Even the vast voids of intergalactic space cannot cool further without limit, because radiation and quantum fluctuations prevent absolute stillness. The third law reminds us that even in the depths of space, motion and energy can never be completely extinguished. The third law also has philosophical resonance. It sets an ultimate boundary that is not merely technological, but fundamental. We can imagine colder and colder states, but there is an absolute floor. In a universe otherwise vast and open-ended, the third law provides a limit that is definitive and inescapable. It reminds us that nature is structured not only by possibilities, but also by impossibilities. At a deeper level, the impossibility of absolute zero connects to the uncertainty principle of quantum mechanics. Even at 0 Kelvin, particles retain zero-point energy, a residual motion that cannot be eliminated. Electrons in atoms occupy ground states, not rest states. Vibrations in crystals persist as quantum fluctuations. These irreducible energies mean that absolute zero is not only unattainable in practice, but non-existent in a strict sense. There is always some motion, some fluctuation, some remainder of activity in the fabric of matter. The third law thus aligns with quantum theory, both pointing to a universe where stillness is an illusion. The study of matter near absolute zero continues to expand our understanding. In recent decades, physicists have cooled atomic gases to billionths of a Kelvin, producing Bose-Einstein condensates. In these states, atoms behave as a single quantum entity, exhibiting coherence over macroscopic distances. Such condensates provide laboratories for exploring quantum mechanics in new ways, from simulating cosmological phenomena to probing the interplay between particles and fields. Again, the third law frames these explorations, defining the boundary that can be approached but not crossed. In practical chemistry, the third law improves accuracy in predicting reaction equilibria. Because entropy can be assigned absolute values, chemists can calculate Gibbs free energies with precision. This allows them to know not only whether a reaction is spontaneous, but also to compare the stabilities of different compounds. Materials design, catalysis, and industrial processes all benefit from this rigorous foundation. The law, born from abstract reflections on cold, shapes technologies that support modern life. At the scale of human experience, the third law may feel distant. Few of us encounter temperatures near absolute zero, yet its consequences touch us daily through technologies, materials, and scientific understanding. It reminds us that even in a world of apparent limits, there are frontiers that challenge human ingenuity. Researchers who cool atoms to billionths of a degree are not defying the third law. They are exploring its boundaries, reaffirming its truth with each step. In reflecting on this law, there is an existential echo. It speaks of an ultimate stillness that can never be reached, a silence that forever retreats as we approach it. Absolute zero is a horizon that beckons but never yields. It tells us that the universe is never fully at rest, that motion and fluctuation persist in every corner of matter. Even at the threshold of the impossible cold, life and change endure. Chapter 7. Engines, Efficiency, and the Limits of Power. The history of thermodynamics is inseparable from the history of engines. Long before the laws of energy conservation and entropy were stated formally, people were trying to harness heat to do work. The first practical steam engines of the 18th century pumped water out of mines, powered factories, and set the Industrial Revolution into motion. Behind their iron pistons and clanking valves lay a profound question: how efficiently can heat be converted into useful work? That question, when pursued deeply, led to the articulation of the second law, the concept of entropy, and the recognition of limits that no ingenuity can overcome. An engine, in thermodynamic terms, is a device that cyclically converts energy from one form into another, usually from thermal energy into mechanical work. To operate continuously, it must exchange energy with at least two reservoirs, one hot and one cold. The hot reservoir supplies energy, part of which is transformed into work, while the remainder is rejected into the cold reservoir. This requirement is dictated not by design flaws, but by the second law itself. No engine can take in heat and convert it entirely into work. Some energy must always be expelled. The measure of an engine's performance is its efficiency, defined as the ratio of useful work output to energy input. For heat engines, the maximum possible efficiency depends only on the temperatures of the hot and cold reservoirs. This principle was first recognized by Sadi Carnot in 1824. Carnot imagined an idealized cycle of reversible processes that defined the upper bound on efficiency. Though real engines could never be perfectly reversible, his reasoning revealed that no engine could surpass this ideal. The Carnot efficiency depends on the temperature difference between reservoirs. The greater the difference, the higher the potential efficiency. Carnot's insight was revolutionary because it detached efficiency from the working substance. Whether an engine used steam, air, or any other medium, the maximum efficiency was governed by temperature limits alone. This universality revealed a profound law of nature. It also suggested ways to improve engines, raise the temperature of the heat source, lower the temperature of the sink, or both. Much of modern engineering can be seen as a pursuit of these improvements, from hotter combustion chambers in jet engines to colder environments for superconducting power devices. Real engines, of course, always fall short of Carnot's ideal. Irreversibilities such as friction, turbulence, heat loss, and finite temperature gradients create additional entropy. These imperfections lower efficiency beyond the fundamental limit. Engineers devote immense effort to minimizing such losses, but even the best designs remain well below the Carnot ceiling. A modern combined cycle gas turbine may achieve efficiencies of around 60%, an impressive achievement, yet still constrained by the laws of thermodynamics. The steam engine, once the symbol of progress, illustrates the principles well. Heat from burning coal transformed water into high-pressure steam, which pushed pistons or turned turbines. Some of the steam's energy became work, but much was exhausted as waste heat. Later designs condensed the spent steam, allowing it to return as water and increasing overall efficiency. Each refinement was guided by an implicit recognition of the laws we now formalize as thermodynamics. Internal combustion engines, which power most automobiles, follow the same principles. The combustion of fuel creates high-temperature gases that expand against pistons, producing work. Part of the energy becomes mechanical motion, while the rest escapes as exhaust and heat. The efficiency of these engines is limited by both the theoretical Carnot limit and practical factors, such as incomplete combustion, heat losses, and friction. Despite generations of engineering advances, their thermal efficiency remains modest, typically below 40%. Jet engines and rockets, which operate on continuous combustion and expansion cycles, also exemplify thermodynamic limits. Their design exploits high-temperature combustion gases expanding through turbines and nozzles, producing thrust. The efficiency of thrust production depends on both the thermodynamic cycle and fluid dynamics. Again, the maximum possible efficiency is capped by the temperature differences and entropy constraints described by the second law. Engines need non-involved combustion. Fuel cells, for example, convert chemical energy directly into electrical work through electrochemical reactions. In principle, such direct conversion bypasses some inefficiencies of heat engines, since it avoids an intermediate thermal step. Yet even fuel cells face limits rooted in free energy changes and entropy. No device can provide work without paying the thermodynamic price of rejecting some energy into less useful forms. The concept of efficiency also extends to refrigerators and heat pumps, which are engines run in reverse. Rather than producing work from heat flow, they consume work to drive heat against its natural gradient. Their performance is measured not in efficiency, but in a coefficient of performance, the ratio of heat moved to work consumed. The second law dictates that these devices cannot move heat without work input. The closer they operate to reversibility, the higher their performance. But irreversibilities always ensure real devices consume more work than the ideal. Thermodynamic analysis of engines relies on cycles, sequences of processes that return the working substance to its original state while producing work. The Carnot cycle, with its perfectly reversible isothermal and adiabatic processes, is the theoretical gold standard. Real cycles approximate it in various ways. The Otto cycle describes gasoline engines, the diesel cycle models compression ignition, the Rankine cycle governs steam power plants, and the Brayton cycle underlies gas turbines. Each cycle incorporates real constraints and approximations, but all are judged by comparison with Carnot's limit. As technology advances, engineers have learned to combine cycles to extract more work. Combined cycle power plants, for instance, pair a gas turbine Brayton cycle with a steam Rankine cycle. The waste heat from the gas turbine becomes the input for the steam turbine, raising overall efficiency. Such innovations reflect humanity's continual effort to approach the thermodynamic ceiling, even while knowing it can never be fully reached. One of the subtler insights of thermodynamics is the distinction between the quantity and quality of energy. The first law assures us that energy is conserved, but the second law reminds us that not all energy is equally valuable. High-temperature heat has more potential to do work than low-temperature heat. Once energy has been degraded into uniform thermal motion at ambient temperature, it can no longer be harnessed. Efficiency is thus about preserving the quality of energy, not just its quantity. Engines, by their nature, always squander some quality, converting ordered energy into disordered heat. Entropy production is the measure of this waste. Every real engine increases entropy overall, even as it produces useful work locally. The energy rejected to the cold reservoir is not lost in the sense of vanishing, but it has become less useful, less capable of further transformation. This unavoidable degradation is why perpetual motion machines of the second kind, engines that supposedly convert heat entirely into work, are impossible. They would require entropy to decrease, which the second law forbids. The pursuit of efficiency is not merely academic. In practical terms, higher efficiency means less fuel burned for the same work, fewer emissions, and lower costs. For societies dependent on energy, efficiency gains translate into tangible benefits. Thermodynamics sets the limits, but engineering ingenuity continues to push devices closer to those limits. Understanding the laws ensures that resources are directed toward feasible improvements rather than impossible dreams. Yet thermodynamics also places humanity's ambitions in perspective. No matter how advanced our technology becomes, no matter how precise our engineering, we cannot escape the ceilings imposed by the laws of nature. These boundaries are not flaws to be corrected, but truths to be accepted. They remind us that, while energy can be transformed, it cannot be created freely, and while engines can be improved, they cannot be perfected. The cosmic perspective reinforces this point. Stars themselves are engines, fusing nuclei at extreme temperatures and radiating energy outward. Their efficiency is constrained by nuclear physics and thermodynamic balances. Even black holes, enigmatic as they are, have thermodynamic descriptions, radiating energy in ways that echo the principles of entropy. The universe operates under the same rules as our simplest steam engines. No energy is created from nothing, and every transformation comes at a cost. At the human scale, the second law and the concept of efficiency affect our own bodies. Muscles convert chemical energy into mechanical work with efficiencies around 20 to 25%. The rest becomes heat, warming our bodies. This waste is not useless. It maintains temperature and supports physiological processes. Still, the limits imposed by biology echo those of machines. We are, in a sense, living engines bound by the same laws. In studying engines, efficiency, and limits, we see both the triumph of human understanding and the humility imposed by nature. We can design turbines that spin at tens of thousands of revolutions per minute, rockets that reach space, and refrigerators that keep food fresh, all by mastering the principles of thermodynamics. But we cannot design a device that surpasses the Carnot limit, nor can we escape the entropy produced by every real process. These boundaries are not obstacles to progress, but the framework within which progress occurs. And perhaps, in the quiet reflection that closes this chapter, there is an existential lesson. Engines remind us that transformation is never free, that every gain carries a cost, and that limits are woven into the fabric of existence. The steam that turns a turbine, the fuel that powers a jet, and the food that sustains a life all obey the same inescapable rules. In recognizing those limits, we glimpse the deeper rhythm of the universe, a balance between possibility and inevitability, between power and its price. Chapter 8. Thermodynamics in the Cosmos. Thermodynamics was born from the practical needs of engines and industry, but its reach extends far beyond factories and laboratories. The same principles that describe boiling water and spinning turbines also govern stars, galaxies, and the ultimate fate of the universe. In the cosmos, thermodynamics is not merely an engineering tool, but a framework for understanding how matter and energy evolve on scales beyond human imagination. The universe itself can be seen as a vast thermodynamic system, with energy exchanges, entropy growth, and temperature gradients shaping its history. The most immediate cosmic example is the Sun. At its core, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. This energy, generated in the form of gamma rays and particle motion, slowly diffuses outward, taking thousands to millions of years to reach the surface. There it escapes as sunlight, sustaining life on Earth. The Sun is a thermodynamic engine, powered by nuclear reactions that reduce the Gibbs free energy of nuclei under extreme conditions. Its efficiency is set not by human design, but by the fundamental laws of nuclear physics and thermodynamics. Stars of different masses follow similar principles, but with varying outcomes. Massive stars burn hotter and faster, exhausting their fuel quickly, while smaller stars like red dwarfs sip their hydrogen slowly and live for trillions of years. In each case, thermodynamics dictates the balance between inward gravitational pressure and outward thermal pressure. When nuclear fuel runs low, that balance is disrupted and the star undergoes transformations, collapsing into white dwarfs, neutron stars, or black holes. Each stage can be described thermodynamically, with energy sources shifting and entropy increasing. White dwarfs represent matter compressed into a state where electron degeneracy pressure resists further collapse. Their thermal glow comes not from ongoing fusion, but from residual heat radiating away over billions of years. Neutron stars push the physics further, supported by neutron degeneracy and nuclear forces. Black holes go further still, collapsing so completely that not even light can escape. Yet even black holes are not exempt from thermodynamics. Work in the 1970s showed that they can be assigned entropy proportional to their surface area and a temperature related to their mass. Stephen Hawking's discovery that black holes radiate thermally unified general relativity, quantum mechanics, and thermodynamics in a profound way. Black hole thermodynamics remains one of the deepest intersections of physical law. Thermodynamics also governs galaxies and galaxy clusters. Intergalactic gas, heated by shocks and radiation, reaches temperatures of millions of Kelvin, emitting X-rays that astronomers detect. The balance between cooling of this hot gas and heating from processes like supernova explosions or jets from supermassive black holes determines how galaxies evolve. Entropy provides a useful diagnostic. Regions of low entropy gas can collapse to form stars, while high entropy gas resists compression. Thus, entropy maps the conditions under which cosmic structures form or stagnate. On a larger scale, the universe itself can be treated as a thermodynamic system. The cosmic microwave background, CMB, is relic radiation from when the universe was about 380,000 years old. At that time, matter and radiation were in equilibrium, and the universe became transparent as electrons combined with nuclei to form atoms. The CMB still bathes the cosmos today, nearly uniform in temperature, but with tiny fluctuations that seeded galaxies and clusters. The spectrum of the CMB is that of a nearly perfect black body, the most precise evidence we have of a system in thermal equilibrium on a cosmic scale. As the universe expands, its average temperature decreases. The radiation cools as wavelengths stretch, while matter becomes more dilute. The entropy of the universe, however, increases. Gravitational clumping into stars and galaxies may seem like a move toward order, but globally it corresponds to higher entropy states. Black holes, with their enormous entropies, dominate the cosmic entropy budget. From this perspective, the universe's evolution is a vast demonstration of the second law, with energy conserved but quality degrading and entropy rising. Cosmic thermodynamics also touches on dark energy and dark matter. Dark matter, though invisible, contributes mass and gravitational effects, influencing how galaxies rotate and clusters hold together. Dark energy, by contrast, drives the accelerated expansion of the universe. Though their exact nature remains mysterious, their behavior must still respect the conservation laws and entropy constraints of thermodynamics. The cosmic energy budget, when tallied, includes these enigmatic components, showing that even the unknown must fit within the thermodynamic framework. One of the deepest questions concerns the ultimate fate of the universe. If expansion continues indefinitely, the cosmos will grow colder and more diffuse. Stars will burn out, black holes will evaporate, and matter will decay, leaving behind a thin soup of particles and radiation. This heat death scenario is the extrapolation of entropy increase to its final limit, a state of maximum entropy where no gradients remain and no work can be extracted. Alternatively, if dark energy changes in character or if other physical effects dominate, the universe might recollapse or rip apart. Whatever the exact endgame, thermodynamics assures us that entropy will guide the path, setting the direction for cosmic evolution. The application of thermodynamics to the cosmos also shapes observational astronomy. Astronomers use the Stefan-Boltzmann law to determine stellar luminosities, Planck's law to interpret spectra, and thermodynamic models of plasmas to understand emission lines from hot gas. Observations of galaxy clusters, the interstellar medium, and the intergalactic medium all depend on thermodynamic analysis of temperatures, pressures, and entropy distributions. Even in cosmology, where general relativity provides the framework for space-time dynamics, thermodynamics provides the language for matter and radiation within that space-time. There is also a remarkable symmetry between thermodynamics and information in the cosmic context. The entropy of the universe is not just a measure of heat dispersal, but of the number of possible microstates consistent with its macroscopic configuration. This links cosmological entropy to questions of information content. Black holes, in particular, raise puzzles about whether information is lost when matter falls into them or whether it is somehow preserved. The resolution of this information paradox is likely to deepen the unity of thermodynamics, quantum theory, and gravity. Closer to home, Earth itself can be viewed thermodynamically as an open system. It receives high-temperature, low-entropy radiation from the sun and emits low-temperature, higher-entropy infrared radiation into space. The difference sustains life and drives weather, oceans, and ecosystems. Photosynthesis, winds, and climate patterns are all thermodynamic processes powered by this flow. The biosphere persists not by defying entropy, but by being part of a larger flow that increases entropy overall. Life is an island of order, maintained by the throughput of energy from a star. Space exploration, too, depends on thermodynamics. Spacecraft rely on radiators to shed waste heat, since convection is absent in vacuum. Cryogenic fuels are stored with careful management of boiling and venting. Instruments on space telescopes are cooled to near absolute zero to detect faint signals. Every mission, whether robotic or crewed, is in part a thermodynamic challenge, maintaining equilibrium, preserving energy, and handling entropy. The study of thermodynamics in the cosmos continues to push physics forward. Efforts to unify black hole thermodynamics with quantum gravity may reveal insights into the fundamental nature of spacetime. Observations of the cosmic microwave background continue to refine our understanding of the early universe's equilibrium. Laboratory experiments with ultra-cold atoms simulate cosmic phenomena, linking the physics of the smallest scales to the largest. The interplay between thermodynamics and cosmology remains one of the most fertile grounds of scientific inquiry. Ultimately, cosmic thermodynamics reminds us that the same laws governing the engines of the Industrial Revolution apply equally to the engines of stars. There is no special exemption for the vast or the mysterious. Energy is conserved, entropy increases, and absolute zero is unreachable, whether in a piston, a supernova, or the entire universe. These laws are as universal as the cosmos itself. And perhaps here lies the quiet existential resonance. Thermodynamics in the cosmos tells us that we are part of a great unfolding, governed by laws that bind everything from atoms to galaxies. Energy flows, structures form, entropy grows, and time moves forward. In this grand cycle, our lives are small but connected, brief sparks in a universe that evolves under the same principles. Even as stars burn and galaxies drift apart, the same thermodynamic truths hold, whispering that change and impermanence are written into the fabric of existence. Chapter 9. Thermodynamics in Life and Technology. Thermodynamics is often introduced through steam engines, pistons, and ideal gases, but its reach is far broader. It underlies the metabolism of cells, the design of power plants, the function of computers, and even the processes that sustain our atmosphere. In life and in technology alike, thermodynamics provides the common framework that links chemical reactions, energy transfers, and efficiency. To understand the living world and the engineered systems that surround us, one must see how the universal principles of energy conservation and entropy apply when energy moves through tissues, machines, and circuits. Living organisms are among the clearest demonstrations that thermodynamics applies universally. At first glance, life seems to defy entropy. Organisms maintain order, build complex structures, and perform intricate functions. But closer analysis shows that life thrives not by breaking the second law, but by being part of an open system. Earth receives low entropy radiation from the sun and emits higher entropy radiation back into space. Organisms are subsystems within this flow. They take in energy-rich molecules and release waste products and heat, increasing the entropy of their environment. The maintenance of internal order is possible only because the overall entropy of the universe continues to rise. Cells illustrate this principle elegantly. They extract energy from nutrients by breaking down molecules such as glucose. Through respiration, glucose is oxidized in a series of controlled steps, each catalyzed by enzymes that channel the released energy into useful work. The cell captures much of this energy in the form of adenosine triphosphate, or ATP. a molecule whose hydrolysis drives muscle contraction, nerve signaling, and biosynthesis. ATP is often described as the energy currency of the cell, but like all currencies, it does not create value on its own. It merely transfers energy obtained from food. The conversion of chemical bond energy into usable work with heat as a byproduct is a clear illustration of the first and second laws of thermodynamics in biology. Even photosynthesis, which appears to create energy from sunlight, conforms to thermodynamic principles. Plants capture photons in chlorophyll, initiating reactions that store energy in sugar molecules. This process is not free. It requires highly ordered arrangements of pigments and proteins to harvest light efficiently. The entropy decrease in the plant's internal structures is outweighed by the entropy increase of the overall process, since Earth re-radiates the absorbed sunlight at a lower temperature. Life harnesses energy gradients, but never escapes the balance sheets of thermodynamics. On larger biological scales, thermodynamics governs physiology. Warm-blooded animals maintain body temperatures within narrow ranges, consuming chemical energy to generate heat. This regulation is an ongoing struggle against entropy. Left alone, the body would cool to match its environment. The high metabolic rates of mammals and birds reflect the constant work needed to offset thermal losses. In cold climates, fur and feathers reduce heat flow. In hot climates, sweating and panting increase it. These adaptations are all strategies for managing energy flows in accordance with the laws of thermodynamics. Ecosystems themselves can be seen as thermodynamic networks. Energy enters through photosynthesis, flows through food webs, and eventually dissipates as heat. Each transfer is inefficient, with only a fraction of the energy passed to the next trophic level. This pyramid of energy reflects entropy's toll on every transformation. By the time energy reaches the top predators, most of the original solar input has already been dissipated. Far from contradicting thermodynamics, ecosystems exemplify it. They are transient structures maintained by constant energy throughput. Technology applies thermodynamic principles in more explicit ways. Power generation is perhaps the most direct. Coal, oil, natural gas, and nuclear fuels all release energy, which is converted into heat. This heat produces steam or hot gases, which expand to drive turbines and generate electricity. No matter the fuel or design, the underlying principle is the same. Part of the input energy is converted into work, and the rest is rejected as waste heat. The maximum efficiency is limited by the temperature difference between the heat source and the sink. Engineers strive to approach these limits by using higher temperature materials, combined cycles, and improved insulation. But the ceiling imposed by thermodynamics cannot be surpassed. In renewable energy systems, the same rules apply. Solar thermal plants concentrate sunlight to heat fluids and produce steam, operating as heat engines. Wind turbines convert kinetic energy of moving air into work, again bounded by efficiency limits such as the Betz limit, which reflects energy conservation and fluid dynamics. Hydroelectric dams transform gravitational potential energy into mechanical rotation and then electricity. These processes are not exempt from the first and second laws. They are simply different ways of exploiting energy gradients available on Earth. Thermodynamics also shapes refrigeration and air conditioning, which are engines in reverse. A refrigerator consumes work, usually from electricity, to transfer heat from a colder interior to a warmer exterior. Its performance is measured by the coefficient of performance, the ratio of heat removed to work input. Though modern devices are highly efficient, they still reject more heat to the environment than they remove from inside, because entropy must increase overall. Air conditioners work the same way on larger scales, moving heat out of buildings at the cost of consuming electrical power. Information technology, though less obviously tied to thermodynamics, is also governed by its principles. Computers consume electrical energy to manipulate information, and much of that energy becomes heat. The heat must be dissipated, often with fans or liquid cooling. The limits are not merely practical but fundamental. Landauer's principle shows that erasing a single bit of information requires a minimum energy cost, ensuring that even computation is subject to entropy. As devices shrink and processing speeds rise, managing heat has become one of the greatest engineering challenges, a reminder that thermodynamics governs even the digital world. Materials science provides another perspective. The properties of alloys, ceramics, and polymers depend on phase equilibria, solubilities, and chemical potentials, all thermodynamic quantities. Steel hardens through controlled cooling, exploiting phase diagrams of iron and carbon. Semiconductors depend on precise control of impurities and defect concentrations, guided by thermodynamic stability. Batteries, too, are electrochemical systems where free energy changes dictate voltages and capacities. Each technological advance relies on understanding and applying thermodynamic principles to matter under specific conditions. Climate science is, at its heart, an application of thermodynamics to Earth's atmosphere and oceans. The planet receives high-quality, low-entropy energy from the sun and radiates lower-quality, higher-entropy infrared energy into space. This gradient drives winds, weather, and ocean currents. Hurricanes, for instance, are heat engines, extracting energy from warm ocean surfaces and releasing it as work and heat in towering storms. The efficiency of such engines is constrained by temperature differences between the sea surface and the upper atmosphere. Climate models depend on conservation of energy and entropy balances to simulate Earth's future. Even medicine finds itself bound by thermodynamic reasoning. The human body's basal metabolic rate reflects the energy needed to maintain temperature and biochemical processes. Nutrition labels on food effectively quantify enthalpies of combustion, the same units used for fuels in power plants. Medical imaging techniques such as MRI rely on superconducting magnets cooled by cryogenic systems, exploiting the third law's domain of near-zero temperatures. Radiation therapy depends on energy deposition from high-energy photons or particles. In each case, thermodynamic principles ensure that calculations are precise and outcomes predictable. Looking to the future, thermodynamics will continue to shape technology. Quantum computers, if realized on a large scale, will require cryogenic cooling and delicate management of entropy. Fusion energy, long a dream, depends on achieving and maintaining high-temperature plasmas with efficiency determined by thermodynamic balances. Nanotechnology will push entropy considerations to new scales where fluctuations matter and stochastic thermodynamics becomes relevant. In all these frontiers, the laws remain inviolable, even as our ability to harness them grows. It is worth emphasizing what thermodynamics contributes to both life and technology. It sets boundaries, but also provides opportunities. It tells us what is impossible, such as perpetual motion or lossless engines. But it also shows us how to approach the possible as closely as nature allows. It explains why organisms require energy input, why power plants have waste heat, why computers heat up, and why climates evolve. It provides the universal framework within which every biological and technological process must fit. And perhaps here lies the existential whisper that closes this chapter. Thermodynamics in life and technology reminds us that we are not apart from nature's rules, but immersed in them. The energy in our food, the power in our machines, and the warmth of our homes are all part of the same flow that moves through the cosmos. Order is sustained only by constant throughput. Nothing is free. Nothing escapes the balance. In this way, our bodies and our technologies are alike, temporary arrangements that borrow energy, transform it, and release it again. We live and build within the same laws that govern stars and galaxies, and in that continuity, we glimpse our connection to the universe itself. Chapter 10. The End of Energy, Entropy and the Fate of the Universe. From the first spark of the Big Bang to the cooling embers of distant stars, the story of the universe is written in the language of thermodynamics. Energy is conserved, yet it is ceaselessly transformed, and entropy grows with every change. While the earlier laws of thermodynamics tell us how energy is accounted for, how temperature is defined, and why some processes occur while others do not, the second law in particular points toward an unsettling long-term consequence: the gradual erosion of usable energy, the relentless increase of entropy, and the prospect of a universe that ends not with a bang, but with a whisper of equilibrium. Entropy is not destruction in the sense of annihilation. It is dispersal, the spreading of energy into less useful forms. A hot star radiates into space, and its photons disperse. A cup of tea cools, warming the air around it ever so slightly. A chemical reaction releases energy, some captured as work, the rest dissipated as heat. In every case, entropy increases, not because energy disappears, but because it becomes less structured, less able to drive further transformations. Over cosmic timescales, this accumulation matters. The question then arises, if entropy must increase, what is the final destination of the universe? One possible fate is called heat death. In this scenario, the universe continues expanding indefinitely. Stars exhaust their nuclear fuel and fade into white dwarfs, neutron stars, or black holes. Over billions of years, these remnants themselves cool, radiating away their last reserves of thermal energy. Black holes evaporate through Hawking radiation on timescales of tens of years or longer. Matter itself may decay, leaving only a thin mist of particles and photons. With no gradients of temperature, pressure, or density remaining, there will be no possibility of work. The cosmos will have reached maximum entropy, a state of equilibrium so complete that nothing further happens. Time, defined by change, would lose its arrow in a stagnant sea of uniformity. This picture is stark but grounded in thermodynamics. For work to be extracted, differences are required between hot and cold, concentrated and dispersed, ordered and disordered. Entropy is the measure of those differences vanishing. In the far future, with all gradients erased, the conservation of energy would remain true, but all of that energy would be trapped in disordered forms, incapable of doing anything new. It is not that the universe would end abruptly, rather it would dwindle into silence, each transformation adding another fraction of entropy until no transformation remains possible. Yet heat death is not the only cosmological scenario, though all are constrained by thermodynamics. If dark energy, the mysterious driver of accelerated cosmic expansion, remains constant, then the heat death model is consistent. But if dark energy grows stronger over time, it could produce a big rip. In this scenario, the accelerating expansion eventually overwhelms all binding forces. Galaxies would be torn apart, stars shredded, planets ripped away, atoms pulled apart, and even subatomic particles separated. Though more violent than heat death, the thermodynamic principle remains. Entropy increases as structures dissolve into ever finer dispersal. Alternatively, if the expansion of the universe were to slow and reverse under gravity, a big crunch might occur. The cosmos would collapse back toward a singular state, heating as it contracts. In this version, entropy does not vanish but is compressed into the final state, perhaps setting the stage for a new cycle. Whether such a cycle could ever truly reset entropy is a matter of debate. Some cosmological models suggest that each cycle would begin with higher entropy than the last, meaning that even in oscillation, the long-term trend remains growth of entropy. Black holes bring another dimension to the discussion. They are paradoxical objects, regions where gravity is so intense that nothing can escape, yet they also carry entropy proportional to the area of their event horizons. The entropy of a single supermassive black hole dwarfs that of all the ordinary matter and radiation in its host galaxy. Over time, black holes slowly evaporate by emitting Hawking radiation. This process releases energy into space but increases the overall entropy further. Thus, black holes act as both entropy reservoirs and entropy factories. In the ultimate future, their evaporation would be one of the final chapters in the universe's thermodynamic story. The third law of thermodynamics, which says that absolute zero cannot be reached, also plays a role in this cosmic fate. Even as the universe cools, it can never reach true stillness. Residual fluctuations, quantum effects, and irreducible zero-point energy persist. There is no perfectly quiet end state, only an asymptotic approach to one. Absolute uniformity is unreachable, but the universe may come arbitrarily close to it, with entropy maximized and useful energy exhausted. The concept of entropy as the arrow of time becomes especially poignant here. On human scales, time's direction is evident in irreversible events: aging, decay, cooling, diffusion. On cosmic scales, entropy's increase defines the direction of history itself. The early universe, though hot and dense, was remarkably low in entropy because it was so uniform. As structure formed, galaxies, stars, planets, entropy increased, even though local order also emerged. The future, governed by the second law, lies in the continual growth of entropy, whether through gradual dispersal or catastrophic disassembly. For technology and life, these cosmic trends may seem remote. Our concerns are with energy supplies over decades or centuries, not trillions of years. Yet the laws that determine the fate of the universe are the same ones that dictate the efficiency of engines and the metabolism of cells. The same entropy that grows as stars radiate is the entropy that grows when a computer chip heats up. The same impossibility of perpetual motion that defines engineering limits also defines the cosmic horizon of time. There is no separation between the small and the vast. The laws are universal. Still, it is important to note that our understanding of the universe's fate is not complete. Dark matter and dark energy are still only partially understood. Quantum gravity, the theory that should unify general relativity and quantum mechanics, remains elusive. It may be that future discoveries alter our vision of cosmic thermodynamics. Perhaps entropy has deeper aspects not yet known, or perhaps new physics allows processes we cannot now imagine. But within the framework we have, the trajectory is clear. Entropy increases, usable energy diminishes, and the universe evolves toward equilibrium. Even if equilibrium is the ultimate fate, the journey matters. The rise of entropy does not mean a monotone universe from the start. In fact, it is entropy growth that allows complexity to exist at all. Stars form, galaxies cluster, planets coalesce, and life emerges in the interplay between order and disorder, stability and flux. The very structures we cherish, Our bodies, our cultures, our planet are transient patterns carved from energy gradients on their way to dispersal. Without entropy increase, there would be no flow, no time, no evolution. The arrow of time makes existence possible, even as it guarantees impermanence. Reflecting on this grand view, thermodynamics offers not despair but perspective. The end of energy as usable work is not imminent. It lies trillions upon trillions of years ahead. Our place is in the middle chapters, where gradients abound, stars shine, and life flourishes. To live is to participate in the great thermodynamics story, borrowing energy, building patterns, and contributing inevitably to entropy's growth. And in the quiet closing thought of this book of laws, entropy whispers that time's arrow moves forward, carrying all things toward transformation. The heat of stars, the warmth of life, the glow of thought itself, each is a temporary concentration of energy, a brief defiance against dispersal. Yet none are exempt. In recognizing this, we see not futility but connection. Every moment is part of the same unfolding, governed by laws as steady as the universe itself. And that brings our journey through thermodynamics to a close. If you're still awake and want to keep traveling through the universe of science, another video is waiting for you here. If your eyes are already heavy, then let them close, and may you have sweet dreams among the stars. Good night, my friend.